The last thing we need to demonstrate that the simplex method actually solves linear programs is some way to prevent cycling. And we saw at the end of the previous lecture that there are sort of two paths that could be followed there. We could find a way of augmenting the method or transforming our LP or something to prevent degenerate dictionaries from existing, or we could, within the confines of the existing algorithm, modify the only places where we make choices. So that would be the pivot selection rule. Both are equally valid paths towards preventing cycling, and there are advantages and disadvantages to both. So there's no reason why the method I'm going to pursue is somehow better. It's just that we need to talk about pivot rules in any case, and there is one pivot rule that we could choose that is guaranteed to prevent cycling, although it has other disadvantages. There are reasons why choosing that pivot rule would actually give you much worse performance than just changing the method, so choosing the other path, so not modifying your pivot selection rule. But in this course, we're going to focus on that, on choosing a different pivot selection rule and using that to demonstrate that under those circumstances, cycling doesn't occur. So maybe we should talk about pivot rules first. The pivot rule we've been using, the pivot selection rule, is what is called the largest coefficient rule. And I defined this right at the beginning when we talked about the simplex method for the first time. I set this up as essentially a choice. If we're looking at a dictionary, we want to choose an entering variable, and we know the dictionary isn't optimal, so we know that there is going to be a pivot necessary to get us to the optimal solution. The largest coefficient rule is to choose among the available candidates, among the variables with a positive coefficient, the one with the largest coefficient. And the logic there was that if we can increase either x or y to increase the objective function, it seems like we get more mileage out of y. If I increase y by 1, then the objective function increases by 2. If I increase x by 1, the objective function increases by 1. So I say, well, I guess I'll choose y as my entering variable. Notice that it's easy to compute this. All I have to do is look at the objective function. No other calculations are needed to choose my entering variable by this rule. That's why I think it's actually a pretty clever and robust rule for a lot of different reasons. It gives us reasonably good performance without too much computation. And so with this dictionary, the largest coefficient rule chooses y. Although x could be the entering variable, the largest coefficient rule will choose y in this case. And so what the largest coefficient rule doesn't consider is once the entering variable is chosen, just because it has a large coefficient doesn't necessarily mean that I can actually increase the variable by that much. That's the key concern. So it's true that yes, if either x or y could be increased to the value 1, then it's better to increase y. But I don't actually know how much I could increase x or how much I could increase y. If I choose y as my entering variable under the usual method, I then have to go looking for leaving variables. And of course I do that by deciding which variable imposes the strictest limit on the value to y. It could turn out that, for example, what if the value that I can set y to is capped at 1/3? And the value I can set x to is actually 10 or something. Well, in that case, x would have been a better entering variable to increase the objective function. So the trade-off is, because the largest coefficient rule only ever looks at the objective function, it can't consider the fact that once you've chosen an entering variable, there's more to it before you know how much you can increase that variable. And so let's walk through the set of pivots that would be necessary and look at them on the diagram. I'll pivot on y, I end up here, and then I just keep going, and I end up hitting the optimal solution up at this corner after hitting 1, 2, 3, 4 intermediate points. Okay, so after 5 pivots, I'm sitting at my optimal solution. And maybe you're staring at the diagram and you sort of know where I'm going to go with the next example, which is, hey, wait a minute. If every pivot is just walking across a vertex of the polytope, and we know that we never walk backwards, then isn't it true that if I start down here and I somehow take this path, I would end up at my optimal solution a lot quicker? And the answer is absolutely. Fortunately, thanks to the magic of contrived examples, there is a very easy way of showing how the largest coefficient rule doesn't necessarily always give you the best result. Not in terms of cycling, just in terms of performance, in terms of not wasting time in the middle. So the question, and I wonder what the answer is going to be, the question is it possible that I can get to the optimal solution from my initial dictionary in fewer iterations? And the answer is, it absolutely is possible. If you can find some pivot rule that takes you along this path, then you'll get there faster. The issue is, can we find a pivot rule that we can efficiently compute? That's the other question. And it turns out this contrived example was in fact intended to answer yes to that question as well. So when we have multiple possible entering variables, the pivot selection rule is basically a heuristic. It's actually a pretty local heuristic. It looks maybe at all the possible, I guess at best, it might look at all the possible places I could end up, and it chooses from among them based on some local criteria. Now, the largest coefficient rule, which is fast to compute, because all it does is look at the coefficient, it just chooses the entering variable based on the coefficient. It doesn't consider how much we can increase the entering variable. There are other rules that exist that use other information. So one example would be the largest increase rule, which goes a step beyond what the largest coefficient rule does. The largest coefficient rule uses the heuristic that the thing with the largest coefficient will increase the objective function the most. But we know that that's not always true. We know that y could end up being capped at some small value, but x could end up being capped at a much larger value, one that outweighs the ratio between the coefficients on x and the coefficients on y. And so the largest increase rule takes that further. It says, choose as your entering variable whichever variable, once you've chosen the leaving variable that goes with it, results in the largest actual increase to this number. And if we think about that, certainly that's a bit closer to what we actually want to achieve than what the largest coefficient rule can do. The problem is it requires us to actually work out every possible choice of entering and leaving variable. So the idea is if I try to increase y, then I end up increasing the objective value by 2. So we know that because we tried that pivot before. If I use y as my entering variable, I get an increase of 2. If, on the other hand, I were to use x as my entering variable, then I get an increase of 7 over 3, which, although we should like fractions by now, is over 2. It's greater than 2. So what the largest increase rule sort of does, there are some ways it can take some shortcuts here, but what it could do is it just could try every possible pivot that's available from this dictionary and just keep the one that results in the largest increase. And you might be thinking about that and think, wow, actually that seems like it could help us resolve cycling as well, because if we try every possible pivot, maybe one of them it breaks us out of our cycle. And yet it actually turns out that the largest increase rule is still prone to cycling. But it's good to at least know that this exists, that there is a rule that would take us across here. And of course, we know once we've gone down this path, because we're in 2 dimensions, there's no way of crossing paths. So we know we're now going to go up here and then hit the optimal solution in 2 pivots. The slide is going to point out what I said earlier, which is, of course, I sat down and made up an LP that makes the largest increase rule look good. So it doesn't necessarily even mean the largest increase rule is good. It just means I found one example where one outperforms the other. And it would be possible to construct an LP where the largest coefficient rule gives us better results than the largest increase rule. And as of this writing, or as of when I'm saying this, I haven't decided yet whether I'll do that in a live session or whether I'll put that on an assignment. So just wait and see what happens next week. We know that the largest coefficient rule is prone to cycling. We saw that in the last lecture. It turns out, despite the fact that maybe you'd think with the largest increase rule, there's more insulation against cycling. Unfortunately, it turns out that the largest increase rule can still result in cycling. So although it's nice to have choices, neither of those choices prevent cycling, which is the great enemy here. I don't care if the algorithm takes more iterations to converge. I just care that the algorithm converges. Obviously, an infinite number of iterations is always worse than a large finite number. So what we want is to consider possible pivot rules. We want to consider whether there is some magic pivot rule that will solve our problem. Now, the problem that we want to solve, I guess we can break it down into 2 parts. One, I would like to be able to evaluate the pivot selection rule easily. So the purpose of a pivot selection rule is to tell me, given the dictionary, what is your entering variable, what is your leaving variable. Ideally, I would like that to be done quickly. I want that to be efficient. And there are reasons why the largest increase rule, I don't want to actually have to do every pivot to compute it, but I have to at least compute a whole bunch of ratios. The largest increase rule, therefore, is less efficient computationally than the largest coefficient rule. We hope if we use the largest increase rule that maybe it pays for itself. Maybe the extra computation at each step is worth it because we end up with fewer steps. So we want to be able to compute it efficiently, and I also, ideally, so if we consider an ideal pivot rule, and I've had to define ideal because there's some theoretical people in the audience will know that a term like ideal needs a meaning. An ideal pivot rule needs to, again, ideally, minimize the total number of pivots. The best pivot rule I can think of, the ideal pivot rule, is one that somehow at every step of my calculation recommends the entering and leaving variable that results in the absolute minimum number of pivots between me and the optimal solution. That is a tough one because finding the shortest path on a polytope between vertices from the initial solution to the optimal one is a global optimization problem. It's the shortest path problem. Whereas when I'm standing at a particular vertex, evaluating all the different edges I can walk along to go to other vertices, that is a local search. Just because this vertex has a larger objective value doesn't necessarily mean, so suppose that I've drawn the vertices of a 3D polytope just sort of out flat on the table here. Suppose I have a situation like this. So suppose that my objective value at my initial point, so suppose the objective value here is 5 and the objective value here is 4, and the objective value at my optimal point is 10. Just because the objective value goes up further when I go in this direction doesn't mean I'm any closer to the optimal solution, because it could be that there are a whole bunch of other vertices between this place here and the optimal solution. So my pivot selection rule does a pretty local search, and it can use heuristics to maybe choose. I mean, obviously we know that I don't want to go somewhere where the objective value is -1, but it chooses the next vertex to visit based on some heuristic. That doesn't guarantee that the next vertex I choose is actually going to be the best possible choice. The ideal pivot rule is one that is somehow able to figure out that this vertex here will get me to my result faster. Unfortunately, we'll see that that ideal pivot rule, I guess, does exist. We just don't really have a way of computing it. So we have two constraints. I want to both be able to compute the pivot, and I also want it to be a good pivot. So here are a list of pivot rules that we ought to talk about. So the one we've been using is the largest coefficient rule. Occasionally it's called Dantzig's rule. So George Dantzig is considered to be the inventor of the simplex method. I'll have some things to say about him when we talk about duality. That would be just choose the entering variable to be the variable with the largest coefficient in the objective function. Okay, fine. Largest increase is work out among all possible entering variables which one will increase the objective value the most in one pivot, and then choose that one. But as I mentioned, in this case, if I start from 0 and I go up to 5, that is the largest increase. It doesn't necessarily mean I'm going to take the shortest path. There is what's called the steepest edge rule, and you might see this called in the literature something called DevX. So DevX was the name of a specific program, a specific solver implementation that used a clever approximation technique to compute this, because it turns out that actually computing this value isn't easy. It's computationally intensive. The steepest edge rule, basically what it does is we know at every step what our objective function is. So I mean, if we had a linear program, recall that if I have this linear program here, I want to maximize 5x plus 3y. We know that the gradient of my objective function is 5, 3. And you can appreciate that maybe if I write this in vector notation, what I'm doing is I'm saying maximize c dot x, where c is equal to this. So that, c equals 5, 3. Can't draw threes. C equals 5, 3, and then x equals xy. So what this is saying is my objective vector c, which happens to also be the gradient of my objective function f, that points in the, we sort of understand intuitively that when we're standing at the maximum solution, the objective vector points directly outwards from my polytope. So it's true that the objective vector does sort of give me a hint as to where I want to be on my polytope. So if I'm standing, I don't have anywhere to draw on this slide, if I'm standing at this vertex here and my polytope stretches out sort of in these directions, and maybe it's in 3D so it sort of goes off into some other dimension as well, my optimal solution is somewhere off in the distance. If I know that my gradient points like this, so my objective vector is c, then odds are the optimal solution is probably somewhere over here. It's probably somewhere, broadly speaking, in the same direction as my vector c, as my gradient. Now, we don't know exactly where it is because we don't know where the vertices of the polytope all the way over here are. If there is a vertex, a distant vertex exactly in this direction, that might be the optimal solution. The steepest edge rule says, basically, choose the edge that you walk along, so whichever next vertex you visit, choose it based on how close it is to this objective vector. So choose the one that's the closest to being parallel to the objective vector. You can look up in both of our books how to do this. So both books give a derivation of how you'd compute the DevX approximation, at least, of the steepest edge rule. It's not pretty. There's a lot that has to be done, and usually it's presented with a linear algebraic interpretation, which we haven't yet seen in this course. But although it seems to be the best rule that is used in practice, it's not perfect for a lot of different reasons, it's still a heuristic. It seems like in practice, if you compare a large library of linear programs, the steepest edge rule seems to be very good. Even it is prone to cycling. So these are 3 performance-oriented pivot selection rules. They choose the entering and leaving variables based on the idea that we want to try and increase that objective function as much as possible, and they're all heuristics. At the other end of the spectrum, we have these rules that don't seem to be performance-oriented at all. So there's this rule here, which says at each step, you've got a bunch of stuff in your objective function. You've got a bunch of possible entering variables. So there's 2x1 plus 5x2 plus 17x3 minus w1 plus 100 w2. And we'll notice that there's a whole bunch of candidates for the entering variable, x1, x2, x3, and there's w2. This rule is pretty true to its name. It's pretty bland. It just says choose the one with the lowest index. Don't even look at the coefficients. Don't look at anything else. Just choose the one with the lowest index. That's it. Doesn't matter. Doesn't matter what any of these are doing. Always choose among the candidates that are available the variable with the lowest index. Sounds pretty bland. Same with leaving variables. If you have multiple candidates for a leaving variable, choose the lowest numbered one. And just like on our assignment, if we've got our x variables and our w variables, we'll just assume all the x variables have a lower number than all the w ones. Okay, pretty boring, pretty bland. There's also the random pivot selection rule, which is you have a bunch of possible entering variables, just flip a coin, randomly choose one. And it turns out, I mean, if you've taken a randomized algorithms course, you know about randomized algorithms, you know that randomness is often really good at helping us with pathological cases. It turns out that the random pivot selection rule actually has some benefits, but it can't completely prevent cycling. It can just make cycling incredibly improbable. And then finally, we have this rule, magic, which is we know that, maybe I still have my diagram here, if I'm standing at this point here, we know that there is a direction I can go in that will take me as close as possible to the optimal solution. Like there is a best pivot that I could make. So let's invent a pivot rule that magically tells me what the best pivot is. At any step, if I'm standing at a vertex, if I'm using the magic pivot rule, it will magically figure out what the best pivot is and tell me what that is. And you can stare at this, the idea of using magic, and think, well, that requires you to believe in magic and magic to exist. It requires both of those two things. And it would certainly help us with this. Actually, I might want that diagram again. It would certainly solve this problem. It maximizes this. It guarantees me that I will always take the smallest number of pivot steps. But of course, it creates a real problem for me here. How do I actually compute the magic pivot? But okay, that's just something I have to work out. We should still allow it to be considered, the magic pivot rule. So I'll just walk through these. So largest coefficient, what are its advantages? Well, the big one is that it's easy to compute. We can do it sort of at a glance. We can iterate over the coefficients of the objective function and we're good. It is a little bit performance oriented because the basic logic behind it, so it was called Danzig's rule because he invented the simplex method and it was the rule he originally proposed. It was considered to be sort of a modest performance oriented rule. Not too much computation needed, but it is a good heuristic. Generally speaking, choosing the largest coefficient can help you increase the objective function. On the other hand, because we don't examine the impact of the leaving variable, just because it has a large coefficient doesn't mean we'll get a large increase, and of course, cycling. So that's a problem. The largest increase rule is harder to compute, but it doesn't require doing that much work. In my earlier example, I demonstrated largest increase by actually trying different pivots and seeing what happened. There is a way of computing the largest increase without actually doing the pivot. All you have to do is look at every possible entering variable, then figure out what the leaving variable would be, and then just figure out that ratio, basically. Figure out the highest, the upper bound on the entering variable. And so it is harder to compute. You have to look at everything in the current dictionary as opposed to just one row, but it has more information to work with, and so it's more performance-oriented. It's more likely to actually increase the objective function. The disadvantage is, yeah, it does have more information on hand, so it's harder to produce a case where largest increase doesn't take us in the right direction. It's still a very local decision. And so actually that diagram I had earlier, this is really paying dividends. Just like I mentioned earlier, largest increase would take us up to this vertex here, which would then take us on a very long path to the optimal solution. So it's a heuristic. It doesn't guarantee that we're actually going to get the shortest path. And so there's also the fact that it is still prone to cycling. So we're still in some trouble there. The steepest edge rule appears in practice, so this is based on empirical analysis, it appears in practice to be more effective than the other rules. It is, however, computationally very expensive. And I mentioned both of our books actually do talk about this, and they typically, it appears as if it's often called DevX, but as far as I can tell, DevX is the name of a specific implementation of it that approximates the steepest edge rule very well. And so both books give a derivation of that, and you can, if you take a look at it, I mean, just flip to the page in the book, look up DevX in the index, flip to the page and stare at the hideous wall of algebra it shows you. That might be enough to convince you that it is a bit more complicated than the largest increase rule. And unfortunately, even despite all the complexity, it still might cycle. So those are the three performance-oriented rules. In my overview slide, I mentioned this. I guess I should actually say it on video. There are lots of other choices of pivot selection rules. And of course, in an implementation, you could combine them. You could use some combination of them to maximize the benefits of one without having any of the disadvantages. And if you want to, and if you're a CSE 545 student and you want to analyze one of them or you want to talk about other ones, that could be your presentation topic. Okay, so steepest edge is considered to be the gold standard in terms of performance, but it's pretty computationally expensive. And I think in practice it's been determined that other than the cycling problem, it's worth the expense. That is, it takes a lot longer to compute it, but in exchange you are likely to follow a much shorter path to the optimal solution, and therefore it's worth doing. Then what about the non-performance oriented ones? So there's Bland's rule. So I called this Bland earlier. It turns out that the reason it's called Bland's rule is that the person who invented its name was Bland. It's actually named after somebody named Bland. I think it's a very fitting rule. If I were named Bland, I would invent very bland sounding rules. So the advantage of Bland's rule is, remember that Bland's rule is choose the lowest numbered variable. If your objective function has, actually let's create a situation where it's even more confusing. So 20x2 plus 5x1 minus w3 plus 100 w4 plus 1000 x4. If this is my objective function, Bland's rule says you figure out the candidates, figure out everything with a positive coefficient, choose the one with the lowest index without any regard to anything. As you can see, that's really easy to compute. All I have to do is look at the objective row and find the positive coefficients and choose the lowest numbered thing. I don't even have to compare coefficients. I just have to find the positive ones. We'll see if we use a linear algebraic representation, it gets even easier to compute because we might actually be using 0, 1 vectors or something. The other advantage of Bland's rule is that it never cycles. It is guaranteed, and we can prove it, that if you use Bland's rule as your pivot rule, you will never cycle. However, because it doesn't consider performance, you could end up wandering all over the place before you get to your objective, your optimal solution. It doesn't cycle, so it'll never go back to a vertex it visited before. The problem is, it might visit every vertex of the polytope because it doesn't make its choice of edge to follow based on performance. And that's the reason Bland's rule can be a bit of a problem. Now, of course, we saw in the previous lecture that it doesn't prevent degenerate pivots, it just prevents cycling. There are lots of dictionaries we could encounter where all pivots that are available are degenerate. So Bland's rule could still make a degenerate pivot. It could even make a degenerate pivot if there are better options. It just guarantees that when the dust settles, it won't cycle. So Bland's rule could, for some reason, cycle through a whole bunch of degenerate dictionaries, but it'll never go all the way around in a circle. And I know that's a sort of bizarre observation to make. The other half of this lecture is a proof of why that's the case. And I'm going to make that a separate video because the proof is absolutely nasty. And I want to allow myself the ability to cut that video together separately. Okay, so then there's the random pivot selection rule. So the random pivot selection rule is, I'm going to actually borrow my diagram here. oh, whoops, I didn't, there we go. So here's my model objective function. The random pivot selection rule is similar to Bland's rule in that we figure out all the candidates for the entering variable, and then we flip coins and just pick one. So we say it's W4. We randomly select one. And this isn't performance oriented because, again, there's no regard to any coefficients or increase or anything else. It turns out that infinite cycling is improbable. So the probability of the simplex method cycling literally forever with the random pivot selection rule, the probability is 0. It's a 0 probability event. Now, those of you that know about probabilities know that just because something has 0 probability doesn't mean it will never happen. And so the random pivot selection rule does prevent cycling in any probable case. And maybe we can appreciate why that is. It's because we saw in the previous lecture that cycling, when I'm working through a cycle, when I'm working through that sequence of degenerate dictionaries, there will be somewhere in the cycle where I can escape. There will be some pivot somewhere in the cycle that I can use to get out of the cycle and return to increasing my objective value. The problem is, if you design an LP for a particular pivot selection rule, you can design it so that the rule always misses that pivot. And so the key with the random rule is because you can't design an LP that predicts random behavior, if I randomly select a particular entering variable at every step, even if it cycles a couple of times, so suppose I had a cycle of length 6, like we saw in the previous lecture, I could cycle around 6 dictionaries, then the same 6 dictionaries again, and then again and again and again. But if every time I'm picking different, I'm randomly selecting pivots, then there is a probability that over time, I will eventually choose a pivot that gets me out of the cycle. And that's basically why we can guarantee that infinite cycling is a 0 probability event with the random pivot selection rule. And the other thing is, assuming that random numbers can be computed, it's really easy to compute your entering variable. You just collect all of the candidates and then choose randomly from among them. That doesn't mean randomness is easy to create or whatever. If you're listening to this and you know about randomness, I'm not claiming that it's easy to get random numbers. I'm saying if you have random numbers, you don't have to worry about anything else besides the whether the coefficients are positive in the objective function to decide what your pivot is. Conversely to the infinite cycling being improbable, if you use random pivot selection, the algorithm will terminate with probability 1. But that isn't quite the gold standard we need. To prove that the algorithm works, we must prove that it will always terminate, not just terminate with probability 1, although we're almost there if we can say probability 1. The other thing is, we'll talk about performance, so not infinite versus finite, but actual asymptotic performance. We'll talk about that in the next lecture. Due to randomization, we'll see that there are worst case inputs to the simplex method for any pivot selection rule. Cases where the simplex method will go through every vertex of the polytope, which could be an exponential number. It won't cycle, but it will go through an exponential number of steps. We know, you might have seen in previous courses, that randomness often allows us to insulate against sporadic worst cases. If the worst case is not likely to occur, then randomness can often make it very improbable that you'll actually see the worst case. Because often worst case examples are constructed deliberately to leverage what we know is deterministic behavior. And when you don't have deterministic behavior, you can't do that. So you do have this advantage of random pivot selection. And I think one of our books, I think the yellow book, actually has some discussions of various implications of randomness, because one of the authors has done lots of research in that area. And it is actually pretty interesting, but there's not enough time to go into much more detail in this course. Then there's this rule, the magic rule. So the magic pivot selection rule is a magic rule that relies on the power of magic to tell you at every step, if I'm standing at this vertex and I've got all these different choices, it will tell you which choice to make such that you are guaranteed to always get to the optimal solution in the shortest number of steps. And of course, that means that you are guaranteed to never cycle with the magic rule. The problem, of course, is that nobody knows how to compute that. I mean, it's a perfect pivot selection rule, except to the extent that I have no idea how to actually implement it. I guess you can implement it by brute force. I suppose if I wanted to know the best choice of pivot from this step here, I could exhaustively enumerate every possible pivot and then recursively do that for every pivot out of that pivot. And I could just look at every possible path between here and the optimal solution, and I could choose the best one. So, I mean, that would be possible. I could just basically compute every vertex of the polytope, work out the relationships between them, and then use a graph algorithm to compute the shortest path. that would be exponential, which of course would defeat the purpose. We have, as it turns out, if I use Bland's rule, which is known not to cycle, in the worst case, I visit an exponential number of vertices. To even compute the next pivot using the magic rule, as far as I can tell, I might have to visit every vertex of the polytope just to figure out what the next pivot will be. So this is the usual issue. It is the case of I want to compute the answer to a global question with only local information. So the magic rule exists, and it's called various other things in the books. The books actually talk about it as well. But of course, we can only use it as a theoretical device. We can't really implement it. And if we could implement it, we could solve a whole bunch of other theoretical problems. So before we can compare them, like before we can talk about actual performance, and I mean in terms of exponential versus linear versus polynomial, we first have to actually prove that the algorithm works. We have to prove that it can solve any linear program. So the next lecture will talk about performance. The rest of this lecture will talk about that, putting this last piece in place, demonstrating that the algorithm actually works. The way we will do that is we will prove that if we choose Bland's rule as our pivot selection rule, then the algorithm will never cycle. So I'm going to make that a separate video. The video will be the proof that Bland's rule doesn't cycle. And as I mentioned earlier, it is nasty. But once we do that, once we get through that proof, we can begin talking about things like, okay, now that we know how to prevent cycling, what can we do to try and make the algorithm take as little time as possible? And that'll be next week's topic.